For these two given linear transformations from R3 to R3, we are tasked to solve for the image and pre-image of specific vectors here. Since we are using here v sub 1, v sub 2, and v sub 3, we can say that they are components of vector v, and hence we are going to solve for its image, that is a element of its codomain. For W, this is already a part of the codomain, so in short, we are going to solve for the pre-image, its equivalent vector v that allowed it to solve for this specific value. So we have two of linear transformations here and here as well. So let's start with the first linear transformation, and we're going to solve for the image of vector v. To solve for that, we'll have the transformation of vector v with the components in R3, v sub 1, v sub 2, and v sub 3. We're just going to substitute here the components of this vector, negative 3, 2, and 5. And using this defined transformation, we can solve for its image. Its image is actually 0, and then v sub 1, in this case negative 3, plus v sub 2, which is 2, and then v sub 2, which is 2, plus v sub 3, which is 5. That would mean the image of the vector v, which with components negative 3, 2, and 5 using this linear transformation, is 0, negative 1, and 7. Again, this is the image of vector v. So it's easier to solve for the image of a certain vector because you just need to substitute the values for v sub 1, v sub 2, and v sub 3 using the definition here. But it will be trickier for us to solve for the pre-image. So W here is a component of or an element of our codomain, and we're going to solve for its pre-image, in short, a certain vector v. We're still going to use the same process here. The transformation of vector v, we'll have v sub 1, v sub 2, and v sub 3 as mentioned here is equal to the entire expression, equivalent 0, v sub 1 plus v sub 2, v sub 2 plus v sub 3. And this should be equal to your vector w. That would mean you will have here 0, v sub 1 plus v sub 2, v sub 2 plus v sub 3 is equal to your w, 0, 2, and 5. Of course, the first entries are 0 because you have here the 0 here. So we're going to solve for the components of a certain v vector. That would mean v sub 1, v sub 2, and v sub 3 here. So we'll have to make the equivalence here. V sub 1 plus v sub 2 is 2. You also have v sub 2 plus v sub 3 is equal to 5. As you can see, we have three different variables here, but we only have two equations. That would mean we are going to represent one as arbitrary constant. So let's pick v sub 3. Let v sub 3 be equal to t. Why do we do this? This means that we have infinitely many vectors here, depending on the value of t, that will get this specific image. So if v sub 3 is if v sub 3 is t, you will have here v sub 2 plus t is equal to 5. So v sub 2 is 5 minus t. And for our v sub 1 here, you have v sub 1 plus v sub 2 is equal to 2. V sub 1 plus your v sub 2 here, which is 5 minus t, equals to 2. V sub 1, you have 2 minus 3, and then your positive t, so t minus 3. Take note that all components of your vector, your image for the pre-image rather for vector w has t. So you can write it like this. Okay, so we'll have here, of course, you can try doing like this. Your v sub 1 is t minus 3. Your v sub 2 is 5 minus t. And your v sub 3 is t. But of course, you can come up with, or you can factor t here. And you will have, you cannot factor t because you will have binomial expressions here and here as well. But you could express this in terms of a set. So you will have the set of this vector t minus 3, and then you will have 5 minus t and t where T is an element of R. Okay? That would mean there are infinitely many possible vectors that are pre-image of your vector W. So this is for our first set. We still have the second set, and let's find out if we have a specific pre-image for W later. But of course, you will start with the image of your vector V. You have V sub 1, V sub 2, and V sub 3. So the transformation of this is your vector V. You have negative 2, 1, and 2. But using this definition here, you will have V sub 1 negative 2 plus V sub 2, which is 1. Then 1 plus 2, and you have your V sub 3, which is 2. Following this definition here, this would mean that your image, the image of your vector V is negative 1, 3, and then 2. Again, it's easier to solve for the image because you already have your definition. For your pre-image, for your vector W, it will have this form. Okay, I'm just repeating this so that we could have a construct. V sub 1 plus V sub 2, V sub 2 plus V sub 3, then V sub 3. This would be equal to your vector W. Okay? So we have V sub 1 plus V sub 2, V sub 2 plus V sub 3, and V sub 3 equal to your W, which is 0, 1, and 2. So equating the two vectors, you have V sub 1 plus V sub 2 is equal to 0. V sub 2 plus V sub 3 is equal to 1. And your V sub 3 is already given as 2. Okay? This is your V sub 3. You already have 2. So it's exact. If we're going to use that value here, so your V sub 2 plus V sub 3 equals to 1. V sub 2 plus 2 equals 1. You will have your V sub 2, which is negative 1. That's negative 1. And for here, V sub 1 plus V sub 2 is 0. You have V sub 1 plus negative 1 is equal to 0. V sub 1 is positive 1. Unlike earlier where we represented our image of W as with arbitrary constant T, we have here exact. In short, or by the way, this is thicker, right? So the pre-image of our vector W, which is vector V, is a vector with components 1, negative 1, and 2. So this is how we solve the image and pre-image of linear transformation under R3 to R3. Thank you very much for watching.